Hello children. So today in this video we will discuss about the part C from chapter 8, that is electrical energy and power. So first we will discuss what is electrical energy. So we already know that what is electrical energy. Here, electricity is a form of energy that produces when charges move from one place to another place. When charges move, we know that it is a current. Flow of charges is known as current. Now, this electrical energy, whatever the energy we are getting from these electrons, is known as electrical energy. This electrical energy can be transformed from electrical energy to different forms. For example, it can be converted to heat, it can be converted to light, it can be converted to sound energy, and there are many different types of energy. By the conservation of energy, by the law of conservation of energy, we know that energy can neither be created and it cannot be and nor be destroyed. Only we can transform the one form of energy into another form. Okay, so that we will discuss here. Here, usually when we start a fan at home, so what we are doing? We are converting electrical energy into mechanical energy. Listen here. The first example is on passing electric current through the heating element, that is through a nichrome wire. What happens of an electric heater, oven or geyser? It gets heated up due to the resistance. We have already studied this one, and the electrical energy has been converted into heat energy, so which is used for the heating purposes. Next one, if we pass electric current through electric lamp, what will happen? The bulb gets heated and it starts to glow. So here electrical energy is getting converted into light energy. The third example is on passing electric current through an electric motor used in a fan, mixer, juicer. What is happening? Its coil and the attachment with the axle of the coil begin to rotate. So it creates a mechanical energy. So the electrical energy changes into mechanical energy here. Next one, when you pass the electric current through electrolyte. So electrolyte we have discussed, that is used in cells. So while charging, what happens? The chemical reaction converts into, while charging, the electrical energy converts into chemical energy, and while discharging, the chemical energy converts into electrical energy, and some part will be converted as a heat energy. Next, if we pass electric pulses from microphone to a loudspeaker, what will happen? Electrical energy gets converted to sound energy. Next, if we pass electric current in a coil, okay, wound around a soft iron bar. So what we are doing here? We are making a electromagnet. So electric field we will pass around the magnet, and we pass around the iron bar. So we will make it a magnet. Okay. So it is nothing but electrical energy into magnetic energy. Okay. So this is about the transformation of electrical energy. Next we have measurement of electrical energy. Here we know that when current I is flowing through the conductor of resistance R, here you can see the current I is flowing through the conductor, it has resistance R, okay, and there is a potential difference, it is connected across the circuit. Okay, so this potential difference, what it does, it helps the unit charge to move from one end to another end. That is, flow of charges is possible from excess of electrons to deficit of electrons. Now we have to find the amount of electrical energy supplied by the source. So due to flow of current I for time t, the amount of charge passed is, so we have already studied this one. So when current I passes for time t, the amount of charge Q is given by, just a minute, I'll show you. This Q is given by Q is equal to I into T. Q is equal to I into T. Okay. So that is current in time T. Next, by the definition of potential difference. So what does the potential difference definition says? It is the work done. Okay, it is the work needed to move a charge Q from through a potential difference V. Okay, from infinite position to that particular point. Okay, so it is the work needed to move a charge Q through a potential difference V. So how we write that one? This W is equal to Q into V. W is equal to Q into V. Now we know that what is this Q? Q is equal to I into T. I into T. Amount of current passing in time T. So it will be IT into V. So what we get? We get W is equal to V into I into T. It gives us the electrical energy. Work done is nothing but energy. So it gives us the electrical energy W, which is supplied by the source. It may be battery or it may be connected to any mains. So in providing the current I for time T in the conductor under a potential difference V. Okay, so under the potential difference, current I is passing in time T. Okay, so that is electrical energy. Next, what we have is expression for electrical energy by the use of Ohm's law. So by using Ohm's law, we are finding the expression for electrical energy. We know that. What does the Ohm's law states? It states that V is equal to I into R. So we know that W is equal to, W is equal to V into I into T, and V is equal to I into R. So in the place of V, if we substitute I into R, so what we will get? I into R into I into T. So what we will get? I square RT. So we are going to get I square into R into T. Now, see here, W is equal to, what is this I square? By this formula, I square is equal to V by R bracket square. So that we are writing here V by R bracket square into R into T. So what we will get? So R will get cancelled. So what you are going to get is V square T divided by R. It is nothing but electrical energy supplied by the source. Okay, and this SI unit of electrical energy is joule. SI unit of electrical energy is joule because it is a form of energy, and usually energy is written in terms of joule. So the SI unit of electrical energy is joule. Symbol is J. Here I am writing that one. Okay. So next what we have is electrical power and its expression. P is equal to W divided by T is equal to V into I. So what is this electrical power? See, electric power is the rate at which electrical energy is supplied by the source. There is a source. For example, source I'll consider as a bulb itself. So what it is doing? Per unit time, whatever the energy that source is producing, that is known as its electric power. So by the definition, electric power is the rate at which the electrical energy is supplied by the source. So there is a source. Okay. So from that source, how much energy is supplied per second? That is known as electric power. So power is equal to, we know that it is energy, electrical energy divided by time. Power is equal to work done divided by time. So electrical energy is nothing but work done. So electric energy divided by time is nothing but W divided by T, work done divided by time. So now work done divided by time is what? Work done is equal to Q into V. So Q into V divided by T we have written. Okay. So next we have P is equal to V into I into T. Okay. P is equal to V into I into T. Why? See here. This W divided by T is power. So this is nothing but QV divided by T. So where that Q went? We know that Q is equal to I into T. We are just substituting this value of Q here, and what we will get? P is equal to V into I into T divided by T. So what we are getting? P, power, is equal to V into I. Now, by the definition of Ohm's law, we know that I is equal to V divided by R. I is equal to V divided by R. So if we substitute the value of V by R here in this equation in place of I, so what we will get? So P is equal to V square divided by R. We are going to get V square divided by R. So again we know that V is equal to I into R. V is equal to I into R. So again in place of V, what I will substitute? I into R. So what we are getting? I into R bracket square divided by R. So that is nothing but I square R. So what we are doing here is we are writing expression for electric power in different forms. So what we are getting? So this electric power is equal to W divided by T. Here the first one. Next V into I, the second one we got here. Next, the third one, V square divided by R. Next, finally what we have? I square divided by R. Sorry, I square into R. So what is this? What is the unit of this electric power? See, unit of this electric power is watt. Unit of SI unit of this potential difference is volt, and that of current is ampere. So the SI unit of electric power is volt into ampere. That is nothing but watt, or you can say joule per second. Okay, so 1 watt is the electric power. See here, P is equal to, we know that, just a minute, I can write it as P is equal to V into I. Sorry. P is equal to V into I. So here 1 watt. Here when P will be equal to 1, when V is equal to 1 and I is equal to 1. That is 1 watt is the electric power consumed when 1 ampere current flows through a circuit which is having potential difference 1 volt. Here which is having potential difference 1 volt. When potential difference 1 volt is applied across the circuit and 1 ampere current flows through the circuit, then whatever the power we are getting, that will be equal to 1 watt. That will be equal to 1 watt. Okay, so there are some different units of this electric power. That is nothing but we have some higher, bigger units. So those are nothing but kilowatt, megawatt, and gigawatt. Okay, so there are some commercial units. Okay, there are some commercial units of electric energy. So what are those commercial units of electric energy? See here, we know that W is equal to P into T, that is watt into second. So watt into second, we can write it as watt into R. So we can write it as kilowatt into R. Okay, so this P, power, is measured in terms of watt, T is measured in terms of second, or it may be measured in terms of R. So this P is measured in terms of watt or kilowatt or megawatt. So what is 1 watt R? So here you can see that the first one is 1 watt hour. Watt hour. Okay, so what is this watt hour? See, 1 watt hour is the electrical energy consumed by an electrical appliance. Whatever the appliance may be, it may be mixer, geyser, heater, whatever. 1 watt hour is the electrical energy consumed by electrical appliance of power 1 watt. Listen here, of power 1 watt when it is used for 1 hour. You are using that particular appliance for 1 hour and it is having the power 1 watt. Then whatever the electrical energy is consumed by it, it will be watt hour. It will be watt hour. Okay, so 1 watt hour is equal to 3600 joule. See here, 1 watt is equal to 1 watt into hour. Okay, watt hour is equal to, so watt is nothing but joules per second into 3600 second. This second and this second goes, so what remains? 3600 joules. Next, 1 kilowatt hour. So what is 1 kilowatt hour? How to define it? See here, 1 kilowatt hour, it is the electrical energy consumed by electric appliance. So consider a fridge. Okay, so 1 watt hour is the electrical energy consumed by fridge of power 1 kilowatt. So the fridge must have the power 1 kilowatt and we should use it for 1 hour. So whatever the electric energy it consumes, it is known as kilowatt hour. Kilowatt hour. Here also what you will get, 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. Okay children, let's study about the power rating of electrical appliances. So every electrical appliance, it has some power rating. Okay, so whatever we are using, geyser, fan, heater, toaster, whatever it may be. So every electrical appliance will have a power rating on it. For example, so let's understand this one. So for example, on a bulb, it is written that 100 watt 220 volt, 100 watt 220 volt. So what does it means? When 220 volts of voltage is supplied, when 220 volt of voltage is supplied, at that time the bulb will glow with 100 watt power. The bulb will glow with 100 watt power. So let's understand this. So this power rating on any appliance will give us the two information. The first information is about the resistance of that particular appliance, and the second information is that how much current should pass through that particular appliance. So how to understand this one? So we have formula for power. It is P is equal to V into I. P is equal to I square into R, and P is equal to V square divided by R. Okay, so let's use the third equation, that is P is equal to V square divided by R. So here we have P is equal to V square by R. So here, what is the power rating of this particular appliance, of this particular bulb? The power is 100 watt. So substitute 100 is equal to, 100 is equal to, what is the voltage? 100 watt. The bulb will glow with 100 watt when 220 volts of voltage is given to it. So it is 220 square, 220 square divided by R, divided by R. So we are finding something, that is resistance of that particular bulb, resistance of that filament. So now if you solve this, you will get it as 484 ohm. Okay, so the resistance of the bulb is 484 ohm. So you have brought a bulb and you are using it in a room. So the resistance of that particular tungsten is how much? It is 484 ohm. So now this resistance will be fixed. As long as you use the same bulb, the resistance of that particular bulb will be same. But what can happen? What can happen is voltage may reduce. Due to the decrease in the voltage, the power of that particular appliance also reduces. Okay, so here by using this power rating, we can calculate the resistance of the particular appliance. Secondly, we can calculate the safe limit or current, how much current we should pass through that particular appliance. So for that we have P is equal to V into I, V into I. So we have to calculate this current. So I is equal to P divided by V. I is equal to P divided by V. So power is how much? Power of this bulb is 100 watt. Power of this bulb is 100 watt. divided by voltage is how much? 220. When 220 voltage is supplied, when 220 volt voltage is supplied, the bulb will glow with 100 watt. So this will give you something 0.45 ampere. 0.45 ampere. So what does it means? Current may change. Yes, due to the change in the voltage, the current in the bulb will change. The current in the circuit will change. So it tells us that when 220 voltage, when 220 volt of voltage is supplied, the bulb will glow with the power 100 volt, and the maximum current which will be passing through that particular circuit, it will be 0.45 ampere. So now what happens when the voltage increases? When the voltage increases, definitely the resistance of the bulb will remain same, because the resistance, the filament will not change. So due to that point, what happens? The resistance will remain same, and only thing which changes is voltage, and with the change in voltage, current also changes. So if the voltage increases, we know that current also increases. So when the current increases, the bulb fuses. Why? Because it is crossing its safe limit, that is 0.45 ampere. 0.45 ampere. Okay, so this is about the power rating of some appliances. So now what is happening in, okay, just a minute. So now what will happen? So now what will happen when this bulb, okay, so when this bulb is brought to home, and now at home we have voltage 110 volt, we have voltage 110 volt. So now also, will it glow with the same power? Will it glow with 100 watt? So that we have to check. Definitely, if the voltage reduces, current also reduces, and power also reduces. So let's check that one. Now what will happen to the resistance? We know that resistance will remain as it is. Resistance will remain as it is, but only thing which is changing is voltage. So which formula we have to use? P is equal to V square divided by R. P is equal to V square divided by R. We know that resistance is same. So what has changed? Voltage has changed. So power is how much? Power we need to calculate. So P is equal to, what is V? Now it is 110 volt. 110 square divided by resistance is 484. Resistance is 484. If you solve this, you will get 25 watt. You will find 25 watt. So what is happening? If the voltage is reducing, then power also reduces. If the voltage reduces, definitely the power of that particular appliance reduces. If the voltage increases, for example, whatever we have discussed, 100 watt, 220 volt. If 220 volt increases, then the bulb fuses, that particular appliance fuses. Now, if the voltage reduces, when the voltage reduces, power of that particular appliance also reduces. So this is about the power rating. This is about the power rating of common electrical appliances. So next, let's go to the household consumption of electrical energy. See here, we are using electrical energy at home. So we are paying for that. So how we are paying? Based on kilowatt hours. Here, electrical meter measures the amount of electrical energy consumed by the various appliances which we are using at home. Okay, so for a given period of time. So every month we are paying the bill. So how we are paying the bill? On what basis we are paying the bill? See here, the electrical energy is sold in the units of kilowatt hour. Okay, so The unit in which the consumer pays the cost of electrical energy consumed is kilowatt hour. Based on kilowatt hour, how many kilowatt hour energy we have used, based on that we are paying to the electric board. Okay, energy is equal to energy in kilowatt hour. So this energy in kilowatt hour is nothing but power into time. So power in kilowatt and time in hour. So power in, if we consider in terms of watt and time in hour, so we are going to divide it by 1000. Next, so this power is nothing but we have the relationship, that is V into I. So power is equal to V into I into T. So that is nothing but, if we want to buy this relationship, which one? V into I into T divided by 1000. So this one. Okay, so it is clear that the total energy consumed by an electrical appliance in kilowatt hour can be calculated by multiplying its power rating in kilowatt with the time duration in hour. Okay, for which it was in use. So now we need to find the cost. So now we are using this energy for some time, okay, for a particular period. Now what will happen? So we have to pay. So how we are paying? So for every kilowatt hour, cost will be mentioned. Cost will be fixed. For example, if the cost for per kilowatt hour is 3 rupees. So how much energy we have consumed? X amount of energy we have consumed into 3 rupees. So this is going to give us the cost of electricity. Cost of electricity. For example, there is an electrical appliance, okay, so which has the power 3 kilowatt, 3 kilowatt hour, okay, and it is used for 2 hours each day, 2 hours each day. Okay, so now the electrical energy consumed by electrical appliance per day will be, so it is 2 hours. So per day, how much? That is 3 kilowatt. Sorry, it is 3 kilowatt into 2. 3 kilowatt into 2 will give you 6 kilowatt hour. 6 kilowatt hour. Next, what we need to calculate? See here. So every day that particular appliance is using the energy 6 kilowatt hour. So over a month, how much energy it has used? We have to multiply this with 30. When we multiply this with 30, we will get 180 kilowatt hour. 180 kilowatt hour. So now if the cost is 4.5 rupees, if the cost is 4.5 rupees per kilowatt hour, so what will be the total cost over the period of 1 month? So it will be 180 kilowatt hour into 4.5 into 4.5. So this will be something, how much? Rupees 810. Rupees 810. So it means what is happening? So the cost of that electricity at the rate of 4.5 per kilowatt, 4.5 per kilowatt, then the total cost will be how much? 4.5 into 180 kilowatt hour. So it will be 810 rupees. 810 rupees. So next we have, if we use the appliances of different powers, for example, the bulb is having power P1, okay, geyser is having power P2, and something fan is having power P3 kilowatt for different duration. They are used for different duration. We don't know the durations. It may be T1, T2, T3 for those respective appliances. Next, the total energy which is consumed in kilowatt hour is the sum of product of power rating in kilowatt and time in duration. For example, the bulb is having power rating P1 and it is used for 1 hour. So P1 into 1 hour, that is T, P1 into T1. Next, P2 plus. We have to add while calculating the total energy. We have to add P2 into T2 plus P3 into T3 kilowatt hour. Okay, so this is about the household consumption of electrical energy. Here we are done. Here we have done with our eighth chapter. So the next chapter we will study in the next lecture. Thank you.